So this particular lab relates to mine ventilations. This is basic fluid flow, and also the use of a dynamic particle size analyzer to work out the particle size distribution of particles for a whole range of reasons in energy engineering. I do want to remind you that a couple of things that we're trying to have you do in the course includes data collection and analysis. This includes uncertainty and propagation of errors. But don't have the idea you're here to collect data. That's an initial step so that you can work out how the data is used. And to do that effectively, you need to know how industry is using the data. And so when you do have an introductory statements, it's very much to be focused on how does industry make use of this information. You should understand decision points, you should understand the rationale for collecting and going through the expense of that data collection so it can be used. Theory very much focus on how instruments work. Note it has nothing to do with methods, it's a standalone segment and it should explain how things work. There's no theory in the mine ventilation lab, and so do need to put a little bit more work into the methods. If you're still not getting the methods right, there is a quiz that you could jump ahead and take. That would be helpful, but many of you are still trying to do step 1, step 2, step 3, and that's not the way it should be written. And so make sure you're using the appropriate style and the methods, and get help if you don't understand what's going on. Effective presentation and communication of the data, including uncertainty. Again, stop and think. Student mode is you ask for data, here's data, did I get it right? Professional mode is here's the takeaway message, and here's the data organized and presented in a manner that supports that assertion. And so many of you are still in student mode, you need to get out and start transitioning to professional mode. You're going to be employed and out of the university in a few weeks. And again, data interpretation, you have to spend your time rationalizing how the data is utilized. It's no good to tell me it's important, no good to tell me it's critical. Tell me how the data is utilized in industry. And you have data, you can do the same thing and utilize it in an effective manner. Effective team function, I've been very happy with the way teams are working, but we can make that process be improved. Give some thought to gender function. Just because there's a young lady in the course doesn't mean she's the one who has to write down all of the data, even though her handwriting is very probably vastly superior to everybody else's. I have daughters. We expect you to be able to function in people from around the world, different genders, and so let's make some progress in that area as well. There are others defined by ABET, and take a look in the syllabus if you're not sure what they are. So, mine ventilation. When we mine coal, it often contains methane gas. And we've done flammability, so you understand flammability ranges from the combustion course. And so if you get methane and air in the volume of 5 to 15%, that's a combustible range, and you can have explosions and detonations. And so that's highly undesirable. Loss of life, loss of instrumentation, loss of the mine location, things like that. And so to prevent that, a lot of the equipment will actually shut down at the 2-3% mark to ensure safety, and of course everyone evacuates. Then there's a loss of functionality, a loss of productivity, in the mine. So we need air to operate in the mines, and we need it to be comfortable for the workers, or at least reasonably comfortable. And so we move air through the mine. It's going to get rid of the methane through dilution. Also any particulates from the mining process. There's dust generated, particularly if you use explosives. There's a lot of dust generated, and perhaps you may have diesel engines underground as well, in which case there's the potential for soot. So what can you do with the methane? It can be captured and used prior to letting it go into the mine shaft, where it gets diluted into that mine corridors where the workers are. So if you can drill down into the coal, extract that methane. You can use if it's very high methane content in the air. use that as combustion air. It gives it a little bit of a boost. So why I'm telling you this is it's one of the reasons, it's not the only reason, but it's why data is collected. There are industry standards, and you should know what these things are. That's a good way of making sure that you're using the data in a realistic manner, the decision points. And so looking for things like that to rationalize how the data is used in industry. And so that requires quality research. You need not to be doing a blind sweep, but going to the right sources to get the right answers. And so you need to have the right strategy. Energy books are the appropriate way to go in most cases. ASTMs are very good starting points as well, just to learn the terminology, etc., etc. But you need to have the right strategy to find this information and be able to do well. So the question you should be asking in your research is, how does the industry utilize this data? So hopefully you're not having lunch or dinner or snacks at this point in time. If you do get particulate exposure, then there's such things called black lung. Even if you're in silica mines, there's something called silicosis, and coal mines that have a higher content of silica have different ventilation rules than regular coal mines. And so exposure to the dust is very unhealthy and can result in this loss of function of the lungs. Coal mining is a significant methane source, and of course it's a greenhouse gas, and so this 18 to 21 times potential per molecule than CO2, has more modes and other reasons as well. We certainly get methane formed during the qualification process, and through the process some of this is collected and absorbed. Our coal bed methane, so this is not associated with mining, but going in to extract the methane, either pre-mining or just as an energy resource in its own right, which is what's normally done. That at one point in time hit about 8% of the natural gas production in the United States. Our natural gas production is increasing dramatically due to shale gas, and so there's been more growth in that area. So this 8% now is considerably less, even though we're producing about the same amount. Obviously, safety issues with ventilation and expense in doing so. And so again, these are some of the reasons why we are interested in the fluid flow in mines. And you've taken a fluid flow class, so go back and give that some consideration. Now this is dated, it gives you an indication that underground coal mines, this one's the abandoned, or coal mining, is a significant contribution of methane emissions in the United States. And so doing something to prevent that is highly desirable. Historically, if we look at mine ventilation, this would be an anthracite mine, and so the air would come in, go around the working faces. These would be typically inclined at 60 degrees, 45 degrees if you're mining into the seam, into the mountain. You'd use explosives, you'd build some chutes, and so the coal would be exploded. You would stand on top of it, do the drilling, load the explosions, empty the coal out, put the chutes in place again, do the blast, and then go through that process. You don't want to have the whole mine ventilated, you just want to get to the working face. And so you control with various means the airflow to take it around to the working face and then out. Some of these means in the early days was a trapper, also known as a nipper perhaps. His job is to open the door whenever the pony pulling the cart appears, and that's there as a baffle to prevent the air from flowing in the direction that is undesirable. Coal mines can be extensive, certainly larger than University Park campus, much more extensive than that in fact. And so as you start moving air around, you need to have a good level of control. So here's a more reasonable, again shown on a very small scale. The real scale is considerably larger, but here you can see the fan. The fan is always offset in case there is an explosion, because it's an important component for the recovery process and could save lives, and so you want to ensure it's not damaged. This one is pulling air. Sometimes there's a secondary one pushing air in, And as the coal gets deeper, coal mine gets larger and larger. Sometimes you swap out and do larger fans or add additional fans in the process to allow you to get the flow that's necessary. In this particular case, you can see that the coal is being mined at this particular face. The clean air is coming in the entryway, is being sent around the working face and is sent out, and there's various permanent and temporary curtains and walls and baffles that are going to prevent the air from going into areas that we don't want to spend money on ventilation somewhere where it's not needed. So what are we doing in the mine ventilation? We are collecting airflow data. We're going to use an anemometer. This is the device you can see in the left hand of the mine foreman. We're going to measure airflow under a variety of settings, looking at how the geometry and other factors influence the flow of air. Just while we're on the subject, a couple other things. If you look at an aerial photograph, these are some of the early days of coal bed methane extraction. So this is unrelated to mining. This is just drilling down into the seam, mostly vertical wells in this particular case. We now do a lot more horizontal wells and hydrofracking, and we can get a bigger volume extracted from a single wellhead. But you can see here they're mostly vertical, given the close spacings of the wellheads. But when you go to a certain depth, the water is going to be salty, saline, and so water disposal is an issue. Obviously there are environmental issues with pipeline construction, traffic and roads, cutting down trees, although not in this particular location. Water disposal, if it's salty water, is a challenge, and of course well spacing here has a very significant impact on this particular location. Of course methane leaks are also highly undesirable. So that's just some background more on fluid flow. Again, no theory for this particular report. The method should be enough that somebody could go and repeat it without who knows what they're doing. So don't say first enter the mine, obtain an anemometer, use the appropriate language like airflow within the mine ventilation lab was determined utilizing a anemometer device. Past tense, technical, go that way. So moving on to laser light scattering. We have a range of particle sizes on the smaller side that we're interested in. Obviously at the top we've got things like pollen and mold and allergens and bacteria and things of that nature. And you can see here the scale here is on a log basis. You've got heavy dust. Dust, I'm not really aware of an official definition. We've always used 100 microns in dust research for mine ventilation at Penn State. So it's particles smaller than 100 microns. Should have the units and of course be labeled. Have this interesting behavior of being suspended and then slowly settling out, and so they can be in the atmosphere for a long time, particularly as you get smaller and smaller. So other dust, smoke, smog, soot, these are all interesting. They're all going to have a range of particle sizes, and essentially that distribution is one of the critical pieces. And so you'll see that I often in the terminology stress distribution. So this is not something where you can do particle size with a mean and a standard deviation, because it does not work that way. So distribution, we need to capture that data in a different manner. So I could think of pulverizers, delivery sizes, catalyst fracturing in a fluidized bed type of arrangement. Certain environmental issues with things like activated carbon. They want to have a relatively narrow particle size distribution. And so there's a large size, typically whole range of sizes, but it's important to think distributions. There are multiple techniques. We'll do some sieving. We're going to do dynamic laser light scattering now, also digital image analysis. So this is some coal particles under the SEM. You can see that with wet sieving I obtained a relatively narrow particle size distribution, and that many of the particles are the same relative size. There is still a range. Obviously, they're not spherical particles, so often we assume spherical particles, so this shows that that's clearly an error. If I do dry sieving, you can see I get a lot of broader distribution. I get some of the smaller particles sticking to larger particles, and that is not particularly good for work involving particle size distribution. The laser light scattering takes advantage of Mie scattering theory, and this is that smaller particles will scatter in a different way than large particles, and so this gives us an indication of particle size. And if we go and look at an instrument, this is not the one that we'll be utilizing. In fact, let me show you this one instead. This one instead. So here we have a suspension of particles in a fluid, in water in this case, where the particles are large enough, and we have a laser passing through. So in the particular instrument we utilize, we control the concentration of the particles. We'd like to have enough that we see a signal, quite a good signal, but we don't want to overload it so that you obscure the scattering. So there is a sweet spot for concentration that we'll utilize. This is showing one laser. Sometimes there are two lasers, and usually multiple detectors. What will happen is the laser hits the particles, the laser light is scattered, picked up by the various detectors. Again, light will fire again separately in sequence. The laser will fire separately in sequence, and you'll get data on information that way. The clever piece in the dynamic scattering is that there is a slight delay in between a few of the pulses, and that allows for the particles to move slightly due to I've forgotten the word. Brownian motion. And so Brownian motion, a large particle won't move very much, a smaller particle will move more, and at the lower level of our particle size distribution, this allows us to extend that range slightly by knowing the temperature of the fluid and doing this Doppler type of this change of frequency because the particles have moved type of property. Again, we don't use this particular instrument, but do look it up and work out how these things work. So what does the data look like? So this is, notice that this is particle size in microns, but it's on a log scale. So while this looks like a normal distribution where you could just drop a mean and a standard deviation and everyone else could duplicate it, you can't do that because of the log scale. So this is a case where I need much more information than a single mean and a standard deviation because the shape of this distribution is not normal or Gaussian or Lorentzian, and so it can be considerably more complicated. So if we look at here, this is the S type of curve. This is the cumulative percent passing, and so I can see the largest particle size here at 100% is here. So about 100% passes through about 20 microns. We do look at the average, and here we look at the D50. This is the middle point of this, or 50% passing, and we can work out that that's going to be somewhere in the 9-8 micron area. And we often do a D90, a D50, and a D10. Often that's called the DV 0.5. The D to indicate diameter, V to indicate that we're doing by volume. So we're not counting the number of particles, we're saying these are the contribution by volume in these particular sizes. Obviously if we went to area or went by number, there would be a considerable shift. So if you think about students in the room, if we did things by weight, you know, there would be a different contribution for some of the students and certainly some of the faculty rather than by simply being a contribution of one. I am larger than most of you, so I would have a bigger contribution. So again, if we go at that S-curve, here's how I would read the D90, the D50, and the D10. We'd work out what size those various pieces are at, and at the minimum we would provide this information. We could also display it as bins, and the blue color is one sample, the red color is a second sample, and so here you can see a histogram, but realize again, because of the log scale, that there is a bigger difference between here and here than here and here. Right? So that's 10, that's 20, whereas this is 9. And again, a couple of different other ways of plotting this out. So, some examples of why we utilize this. So, propant, we know that propant, we would like it to be spherical particles. We'd like it to be narrowly sized. If I had a distribution of particle sizes, I would plug these open spaces with smaller particles, and my fluid flow would be impacted. Activated carbon, obviously in your Brita filter you don't want to wait a day for the water to filter through, and so there's various sizes in which we can control the permeability, and so different things have different size ranges. It doesn't have to be coal, doesn't have to be activated carbon, it could be catalyst particles, it could be other things going on. We're going to make some assumptions about particle shape when it comes to scattering. We're going to make other assumptions too, such as is it transparent, etc. These are things that need to go into the method so things can be repeated. But when we do a digital image analysis, we'll come back to spherical particles. There are some instruments out there that do this type of work, not through laser light scattering, but through digital image analysis. This is one. And so we will actually look at some of that data as well. We're actually using a Microtrack S3500 for our laser diffraction. What's not shown here is the mixing side of things, where we work out the concentration, we use some ultrasonic energy to break up agglomeration, and we pump the material from the concentration dilution setup to get into the fluids into the working zone here prior to analysis. Typical data sheet will show you those two curves. There's the S curve, there's the histogram. You can see most of the particles here are between probably 20 and 100 microns, but we can get the data from some of the statistics. But at least report the D90, the D50, and the D10, and often should also discuss what the shape of the distribution looks like as well. Anyway, spend some time looking up particle size distribution, and why it's important. Don't just look up particle size. That distribution is quite critical. So fluid flow is in 119 Steidl. We're going to climb down a ladder. And so make sure that you let me know if you're claustrophobic or if you have any issues with doing that. Particle size distribution is in 141 Hosler. Go past Pispati's office, past mine. When you get to about Dr. Luking's office, turn right. It's that hidden hallway in Hosler. And that's it.